I had a viewer ask me about stepper motors and how you would control them with a microprocessor. So I thought I'd talk about stepper motors. It's actually one of the very, very first things I ever had to control with a microcomputer. Was actually an 8085. I built a embedded system, which was really, really new back in the day. It was a piece of test equipment that had motors and solenoids and stuff, and it was controlled by a microprocessor, a very new, novel thing. And this was back in 1980. And I used an 8085 microprocessor. That was my favorite in the time. And I had to control some stepper motors. And back then you couldn't buy stepper motor controllers. You kind of had to invent your own. And maybe you could, but it wasn't cost effective to, I guess. But so I learned about stepper motors, and I learned to control them, and how you step them, how you microstep them, how you accelerate them and decelerate them. And I had a whole bunch of learning experiences back in the way back days. Yeah, let me talk about stepper motors. And I pulled this one out of something. I don't even know what it's out of now, but it's a nice, simple stepper motor of a particular type that are easy to understand. So that's the one we'll start out with. And I can operate this one at 5 volts. It's actually a 12-volt motor, but it'll step at 5 volts. So it'll be easy to drive and a good learning exercise. So what is a stepper motor? Well, it steps, right? It doesn't. You turn it on, it doesn't just go round and round and round and round. It only steps one thing. And the way that it does that is it has an armature, which is the part in the center that, if this is the axle, the part in the center that spins around. And it has a bunch of magnets, and let's call these permanent magnets, and let's call these electromagnets, okay? And so there's going to be different ones. There's going to be A, B, C, and D, okay? And these are different windings on the armature. And so if we energize the A winding, we'll have magnetism between these two, and it'll go, right? And then if I turn off A and I turn off B, B's going to kind of want to go here, and it'll kind of move it over a little bit. I'll turn off A and turn on B. Or I can turn off both A and B, and it'll kind of go halfway between, right? It'll go, and then if I turn off A, then it goes the rest of the way. And then I can turn on C. Remember, this thing's rotating. It's actually rotating this direction now. My arrow's not correct from the way I'm explaining it. It's rotating this way. And then it'll be over a little bit, and then we'll turn on B and C together, and it'll go kind of between these two. And then we'll turn on C, and it'll finally go here. So we've gone from 1 step, 2 step, 3 step, right? And so that's the way a stepper motor works. And so you need to figure out how many steps your motor is. It might be a 200 count motor, so it takes 200 steps to go all the way around. Or it might only be a 16-step motor. It only takes 16 steps to go around. You buy them by how many steps that you want. And you buy them how big you want, how strong do you want it, how much current it's going to take and how much voltage it's going to take and things like that. But that's a stepper motor, okay? And so we have to do this, right? And by the time we get A, B, C, and D, we're kind of back in sync again, and then we're just going to repeat. And then this is going to be A, and this is going to be B, and this is going to be C again, right? And it's going to go around. So every 4, it repeats itself. So A, B, C, D, A, B, C, D, and then E is going to be A. So A, B, C, D, A, A, B, C, D, A, right? And so what is the sequence to turn things on and off, okay? So we have the A winding, the B winding, the C winding, and the D winding, okay? And so we might want to have, let's say, the A winding and the B winding together, turn those on at the same time. And then we'll turn the B winding and the C winding together. Okay, so we'll call these zeros. So this will be 0, 0, and this will be 0, 0. Okay, so we'll step, step, and then we go 0, 0, 1, 1, right? And then we go the next one, which is the D winding and the next A winding together, right? And so it'll be 0, 0, 1. What would be a 1 is actually folded around, so it's a 1 over here again, right? So 2, 2, 2, 2, 2, 2, keeps going, 2, 2, 2, 2, 2, 2, 2. And it just wraps around. So the last one's a bit funny. So it's 2, 2, 2, 2. All right? So this is the sequence that we want. And so if you're going to control this with a microcontroller, you might have some type of matrix. We'll call it M. And the matrix might be indexed in 4s. Okay? And the first thing will be 1, 1, 0, 0, comma, 0, 1, 1, 0, comma, 0, 0, 1, 1, comma, 1, 0, 0, 1, comma, or close brackets, right? So you might have something like that. And then if you do M0, you know, you might have this one, M1, you might have this one, M2, M3, right? So so you just have to have an index, 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and you just step into this thing, or 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and you would step in your matrix and you'd be done. So I could have done a video like that. It would have been super boring and not my style of things. And so let's do it all in hardware, okay? Let's try to do the stepping in hardware. I think that'd be much more fun. So how would we step it in hardware? Well, let's take a look at the motor to begin with. Let's take a look at the hardware, okay? So here's a motor, okay? And on this motor, there's 5 wires, okay? 1, 2, 3, 4, 5. And if you take an ohm meter, in fact, let's do it. My favorite ohm meter now, because it's nice and big and we can see it. Okay, so there's ohms. Okay, so we are going to measure ohms. So we will start on one winding, and we'll measure to the next winding, and we get nothing. Really? Oh, it helps. I was using milliamps. It helps if you have it over here in the ohms mode. Okay, so let's go back. Go. Okay, so first winding we have 116 ohms. The next winding we have 118 ohms. The next winding we have 118 ohms. The next winding we have 116 ohms. And the next winding we have, ooh, different, 58 ohms, okay? So that one's different. So let's leave the test lead on that one. And let's test all 4 of them. So this one is 59 ohms. The next one is 60 ohms. The next one is 57 ohms. The next one is 58 ohms. So they are all 60 ohms referenced to this one wire. So if you look inside the motor, there's going to be windings, okay? So there's going to be 4 windings. And then what's the 5th wire? Well, the 5th wire is the common, okay? And so we are measuring these 5 wires. And we found that if we went between these, we were getting 116 ohms. But if we went between this one and this one, it was 60 ohms. So 60 ohms here, 60 ohms here, 60 ohms here, and 60 ohms here. So each one of these windings is 60 ohms, okay? So that's the way you can kind of figure out if you have a motor and you don't know what the pinout is, you can just do it, use a voltmeter and kind of trace it out and figure it out. So we have a yellow, black, brown, and orange, and red. Okay, so jot it down. You know, the red wire is the common. And what we're going to do in order to run this thing is we're going to put the red wire at +5. And then if we ground any of these windings, that will energize them, right? So grounding a winding is energizing, okay? And so we can use transistors or relays or something to turn each one of these on, right? Okay, so let's take a look at how we're going to do that, all right? So I still can conserve some paper. So I'm going to use transistors, okay? So I'm going to have 4 transistors. And I'm going to use FETs. FETs are really nice because they have a very low on resistance. And so I'm going to, each one of these is going to be ground, and then we're going to connect these to the windings. So each one of these will be on the windings. So now we have a way to turn on each of the windings. And we know it's only 60 ohms. Okay, so we can get out a calculator. Okay, if we have 5 volts and we have 60 ohms, that's only 83 milliamps. Okay, so each one is max 83 milliamps. So that tells us how big of a transistor that we need. Okay, and we need something can handle at least 83 milliamps. And so we're going to use a 2N7000. Very popular part. Get them dirt cheap these days. These are good for 200 milliamps, okay? And the nice thing about the 2N7000s are that you don't need anything else. You don't need a resistor, you don't need anything. You can just hook them right up to the microprocessor. So just zeros and ones, 0 to 5 volts on the input, turns it on and off. That's all you need. Don't need any resistors, don't need anything else, just boom, you're done. So that's what we're going to do. And I've built a little board here, and it has the four transistors. And I can zoom in a little bit on that. It has the 4 transistors, and it has four gates and 4 drains, and then all the sources are hooked together up. So we can hook them up to a ground. So I've got that little board ready to go. All right. So now all we need to do is we need to figure out how do we generate this weird sequence of data. All right. And like I said, oh, wait a minute. I jumped the gun. Let's go ahead and turn on the motor all just with wires. Okay, we can do that. All right. We know it's 5 volts, so here's 5 volts. So I'm going to put 5 volts on the red wire, and then if I ground one of the windings, it's going to move. Did you see it move? And I'm going to ground the next wire. Oh, and it kind of jittery. Now, if I do it in sequence, look at that. Isn't that kind of cute? I'm doing these in sequence, and I'm not doing 2, 2, 2, 2. I'm doing 1, 1, 1, 1. The motor still operates. It's not going to be very good for torque. It's not going to have a lot of strength doing it that way. You really need to energize 2 windings at a time, the way that these motors are constructed. But if I just kind of brush the, oops, can you see that? I'm sorry, I'm kind of out of camera here. If I just brush the other wire here against these leads, I'm just grounding 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 as I brush them across, and the motor is moving. So that's kind of what we need to do. But we're going to be more sophisticated about it. We're going to do that 2 at a time thing, all right? So now that we know the motor works, and we know how much current we have, and we know what kind of design we want, now we need to make those 1s and 0s, all right? Okay, so how are we going to make those 1s and 0s? All right. So what I'm going to use is I am going to use a programmable logic device, okay? So before microprocessors, there were things like PALs and GALs and things like that. And we're going to use one of those. We're going to use a GAL, okay, which is a gate array logic, GAL, I forget. So we're going to use a GAL, 22V10, which means there are 22 inputs and 10 outputs, okay? And we're going to do combinational logic, all right? So how do you do combinational logic? Well, first of all, you need a clock. So you need a clock coming in, okay? Okay, well, how are we going to make a clock? Well, 555. We'll use 555 and we'll make a clock. All right, the clock comes into the GAL. So here we are in the GAL, all right? And the output of the GAL is going to be our A, B, C, D, okay? And we want it to go in sequence, so we want to have a 1, 0, 0, 1, a 0, 0, 1, 1, a 0, 1, 1, 0, and a 1, 1, 0, 0, and then a 1, 0, 0, 1. We want to repeat. We want to repeat these things, right? Okay, so we have a sequence of things. So we want a sequencing, right? So we're going to have a counter in there, to keep track of where we are. So we'll have 1, 2, 3, 4. We only need to keep track of 4 things. So we can have a 2-bit counter. We can have Q1 and Q0, okay? And so we're going to have a 0, 0. We're going to have a 0, 1. We're going to have a 1, 0. Or we're going to have a 1, 1. And then it will repeat, right? And whenever we see 0, 0, we want to output that. Whenever we see 0, 1, we want to output that. And 1, 0, output that. And 1, 1, output that. So this is like our indexer into our C code, right? Index into our matrix C. And we need to do this all in hardware, okay? So we need to figure out each one of these, right? This is if I look at this, this is actually going to be A, B, C, and D, right? The least significant. Anyway, it goes this way, right? Okay, so how do we think about this logic? Okay, we could look at the columns, okay, and let's look at the B column, okay, the B column. It's doing a 1, 1, 0, 0, 1, 1, 0, 0. Well, is there anything over here that looks that way? 1, 1, 0, 0. If you look at the Q1 and you invert it, 1, 1, 0, 0. So B is just going to be equal to Q1 inverted. That's all there is to it. So that's an easy one. Okay, we can look around. Anything else funny going on? Oh, look at D. D is 0, 0, 1, 1. D is exactly Q1. It's the opposite of B. So you could express D as equal to Q1, or you could say D is equal to not B. Okay? Either one of those statements is true. Then let's take a look at one of the other ones. We have a, let's look at this one, C. 0, 1, 1, 0. 0, 1, 1, 0. 0, 1, 1, 0. Now, if you know what an exclusive OR is one or the other, but not both. So this is exactly an exclusive OR. 0, 0, there's no ORs there, so that's a 0. 0, 1, there's an OR, there's a 1. Here's an OR, there's a 1. And oops, they're both the same, so we'll make that 0. So this is an exclusive OR. So we're going to say that C is equal to Q, 0, exclusive ORed with Q, 1. Okay? And then we still have to have A. What is A? A is, oh, wait a minute, look at this. If you look at A and C, they're exactly the opposite. So we can say that A is not C. Okay? So here's all of our logic equations, right? You imagine this as a Carnot map or something, but these are all the logic equations, right? B is not Q1, D is Q1, D is not B, and C is, or you can do either one of these, right? You have your choice. Let's do this one. So we'll say D is not B. And then we'll say, I got ahead of myself, not B, okay? That's the way you do it in the programming language, but it's not B, right? D is not B. C is exclusive OR of 0 and 1, and then A is not C. Okay, so now we need to program, all right? So we are going to program in a language called WinCouple, okay? And this is WinCouple. And we're going to be programming the G22V10, so that's our device. And it's our stepper motor driver. We're going to use pin 1 as the clock. That's the way that the G22V10 works. You can't just use any old pin. We're going to be using pin 1 as clock, all right? And then there's a whole bunch of D flip-flops. Sorry, can you see that? D flip-flops in there, right? And so we are going to tell it the output pins. We're going to say we're going to have Q1 and 0 on pins 14 and 15. And that'll be our counter. And then here's where we define the counter. Now remember, a counter, a D flip-flop counter, okay? Here's your clock. and here's Q, and here's not Q, and here's D. And if you take not Q and you put it into D, then it's a counter. It's a divide by 2. Okay? And so we're saying here that Q0's D input, that dot D, is going to be not Q0. So this is Q0, and its own D is its own not. So the exclamation point is not. So not Q0. So this defines the first count. Every single time you get a clock, it'll change states. Flip, flop, flip, flop, flip, flop. Okay. And then Q1 is going to be Q0 and Q1, the D input, are going to be exclusive ORed. So that's kind of a trick to make counters, okay? It's going to say it will change, it will be a 1 if Q1 is a 1, it'll be a 1 if Q0 is a 1, but it won't be a 1 if they're both the same. So 0, 0, and 1, 1, and it won't change state. So that's the way you make a 2-bit counter. So now we have Q1, Q, so these are going to count 0, 0, 0, 1, 1, 0, 1, 1. This is Q0, and this is Q1. So now we have that programmed into our device. And then there's a reset on these things. There's a reset and there's a preset. And I just like to make sure the resets are defined to 0. And so I just say that the reset is 0 and the reset is 0 on those two things. All right. And then we're going to define some more pins. 16 through 19 is going to be M0 through M3, which is our ABCD. And it's going to have the sequence 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, and 1, 0, 0, 1, because that's the sequence we're going to get for our 1, 2, 3, 4. And we're going to use our equations over here. We're going to say that M0 is not Q1, and that's kind of our C thing here. We're going to say M1 is M0 and Q0 and Q1 exclusive ORed. The $ is exclusive OR. And we're going to say M2 is not M0, and we're going to say M3 is not M1. So it's very, very simple. Just that little bit there gives us this count sequence that we want. All right, so let's go over and see if it works. So if you haven't seen this thing before, let me pull it out of the circuit here. I just found these the other day. These are the cutest little 555 module I've seen on eBay. And so there are 3 pins, power, ground, and out. And then the little 5.5 is there, and then there's a pot on the back, and that's it. That's your whole 555 circuit. So yeah, it's really good to connect in the circuit. So we will put it in here in a circuit. Let's see, it goes in here like this. Yeah, okay. And so here is our GAL, our 22V10, and I just put a bunch of LEDs on the output so we can watch things work. So let's get our 5 volts. Here's our 5 volts. And let's see if we does anything. All right, so the lights are flashing, lights are flashing. Okay, so what do all these flashy lights mean? Okay, so let's take a look at the first 2. Okay, so the first 2, 1, 2, 3, 0. 1, 2, 3, 0. So that's Q0 and Q1, okay? Q0 and Q1. 0, 1, 2, 3. Okay, so it's counting to 4. All right, now the next 4, we'll hide those 2. The next 4 are our sequence. So it's 2, 2, 2, and the outside 2. So it's doing exactly what we want. 2, 2, 2, 2, 2, 2, 2, 2, 2. So it's doing exactly what we want. All right. So we have successfully built a stepper motor controller. All right. So if we hook this up to a stepper motor, it should spin. All right. So I need to take some time and hook up our LED or our FETs and hook up the motor, and let's see if this thing will make it spin. All right, there we go. I've put the little board here that has those 4 2N7000s, and I think you can see that the motor is stepping. All right. And so let's see if we can't get the 555 to move a little faster. I don't know how fast this 555 will go. I've never tried this before. Let's see, is that going faster or slower? It's going faster. There we go, look at that. Perfect. So super cool, right? So we've built a hardware-based stepper motor controller. And yeah, let's turn it down so we can watch the little LEDs go. It's kind of fun. Can you see that? Those LEDs. Very fun. I like it. Anyway, this has been a super cool project. I really enjoyed it. It takes me way back from when I did this kind of thing. Now, if you wanted to rotate the opposite direction, instead of stepping 1, 2, 3, 4, you'd step 4, 3, 2, 1, and it would go back the other direction. And if you're clever, you could program the gal to have a direction pin. So if the pin was high, it would go clockwise, and if the pin was low, it would go counterclockwise. That would be an easy thing to add to the truth table. And that's kind of what these things do and how they work. Now there is ways to do microstepping, which, like I said, we're doing 2 at a time, 2 at a time, 2 at a time. You can do 2 and then 1 and then 2 and then 1 and then 2 and then 1, and you can get it to half step. And while you can step in finer steps, it doesn't have a lot of holding torque in those in-between steps, so you can only use it in certain applications. But yeah, this is a full step motor driver right here. And it works great. And it's, like I said, it's been really, really fun. Hope you enjoyed it. Hope you learned something.